Welcome to this problem walkthrough. Today, we'll dive into problem number 316, titled Remove Duplicate Letters. In this problem, we'll explore how to construct the smallest lexicographical string by removing duplicate characters, ensuring each appears exactly once. Let's get started. In this problem, you are given a string S composed of lowercase English letters, and your task is to remove duplicate letters so that each letter appears only once in the resulting string. However, there is an additional requirement: the resulting string must be the smallest in lexicographical order among all possible valid results. For example, consider the input string S equals cab. Here, the goal is to process the string and ensure that each letter appears only once while also producing the smallest possible string in lexicographical order. The constraints specify that the length of the input string will range from 1 to 10,000, ensuring that the problem is computationally feasible for large inputs. Once we process the string based on these rules, we will return the resulting string as the output. For the first example, where the input string is S equals cab, the output is ABC. Here's why: the input contains duplicate letters B and C. To meet the requirement that each letter appears only once, we remove the duplicates and are left with the unique letters of B and C. Among all valid results, the lexicographically smallest arrangement is ABC, so that is the output. Now, let's look at another example. If the input is S equals back, the output is ACB. Here, the input string contains duplicates of C and B. By carefully removing duplicates while maintaining the smallest lexicographical order, we get the result ACB. In the case of the input S equals back, removing duplicates gives ACB, which is the smallest lexicographical sequence among all valid results. Moving forward, let's consider the problem constraints and some edge cases. The constraints ensure that the input string will always have a length between 1 and 10,000, and it will only consist of lowercase English letters. For edge cases, if the input string contains all unique characters, such as S equals ABCDEF, the output will simply be the same as the input since no duplicates need to be removed. If the input string contains repeated characters in sequence, like S equals AAA, the output will be A, as only one occurrence of the character is kept. Finally, for strings where reordering is required to achieve the smallest lexicographical sequence, like S equals ECBA, the output will be ABCDE, as we must rearrange the unique characters to meet the lexicographical requirement. To solve the problem of removing duplicate letters while ensuring the smallest lexicographical order, we first considered two initial approaches. The brute force approach involves generating all possible subsequences of the string that contain each letter exactly once. From these, we select the smallest lexicographical result. While this method aligns with the problem's requirements in theory, it is computationally infeasible due to the exponential number of subsequences generated, making it impractical for larger inputs. Next, we considered a greedy approach with sorting. Here, we count the frequency of each character and use sorting to prioritize smaller lexicographical characters. The idea is to iteratively decide whether to include a character based on its frequency and order. While this improves performance compared to brute force, the sorting step introduces additional complexity, and the approach is not as efficient as it could be. These trade-offs led us to explore a better alternative that avoids unnecessary overhead while directly addressing the problem's constraints. The optimized greedy approach with a stack resolves the inefficiencies of the earlier methods. In this approach, we use a stack to construct the result incrementally. A frequency map tracks how many times each character appears in the input string, while a set helps us keep track of characters already included in the result. As we iterate through the string, if the current character is already in the result, we simply skip it. Otherwise, we check the top of the stack and remove characters that are lexicographically larger and still have occurrences later in the string. This ensures that the stack always contains the smallest possible characters in order. We then push the current character onto the stack and update the frequency map to reflect its usage. This process guarantees that every character is included exactly once while maintaining the smallest lexicographical order. The beauty of this approach lies in its efficiency. Each character is pushed and popped from the stack at most once, resulting in an O(n) runtime. By avoiding sorting and unnecessary computations, this method is both elegant and directly suited to the problem's requirements. The optimized greedy approach with a stack was chosen as the final solution because it achieves the best balance of efficiency, simplicity, and correctness. With a linear time complexity of O(n), it scales well for large inputs and ensures that the constraints of lexicographical order and uniqueness are met. Key insights that make this approach effective include recognizing that smaller lexicographical order can be achieved by removing larger characters that still appear later, and that a stack is ideal for maintaining order while dynamically removing unnecessary characters. The frequency map plays a crucial role in ensuring that no characters are missed. The aha moment for this solution was realizing that greedy decisions, combined with the stack structure, allow us to resolve the problem efficiently without relying on additional overhead like sorting. This approach stands out as the optimal solution, addressing all requirements in a clean and intuitive manner, with no significant trade-offs to efficiency or clarity. To solve the problem, we need to construct the smallest lexicographical subsequence of a given string S such that each character appears exactly once. A subsequence, remember, is formed by deleting 0 or more characters from the string without rearranging the order of the remaining characters. The final result must satisfy 3 key requirements. Every character from the original string appears exactly once, the relative order of characters must be preserved, and among all valid subsequences, the one with the smallest lexicographical order should be chosen. These requirements present several challenges. Specifically, we need to ensure no duplicate characters appear in the result, maintain the correct order of characters, and do so efficiently while minimizing computational overhead. To address this, we'll use a greedy approach combined with a monotonic stack, which allows us to efficiently construct the result while adhering to all the constraints. The algorithm begins by tracking the frequency of each character in the string. By traversing the string once, we can store this information in a dictionary called frequency, where each character maps to the number of times it appears in the remaining portion of the string during the iteration. Next, we maintain a set called in_stack to track which characters have already been included in our result. This ensures that no character is added to the result more than once. The core of our approach relies on a monotonic stack, which we use to build the result string. The stack helps maintain the lexicographical order of characters as we process the string, all while ensuring that the result satisfies the problem's constraints. By combining these tools, we can achieve an efficient and structured solution. The next step is to iterate through each character in the string S. For every character C, we first decrement its frequency in the frequency dictionary since we've encountered it. If C is already in the in_stack set, we can safely skip it because we only want to include each character once. Otherwise, we evaluate whether C should be added to the stack. If the stack is not empty and the top character of the stack is lexicographically greater than C, and that top character still has occurrences left in the string, we remove the top character from the stack. This ensures that the resulting subsequence remains lexicographically smallest. We also remove the character from the in_stack set when popping it from the stack. Finally, we push C onto the stack and mark it as included in in_stack. Once all characters are processed, we convert the stack into a string to form the final result. This algorithm works because it makes a greedy choice at each step, selecting the smallest possible character that ensures the final result is valid. The monotonic stack is central to this process, as it helps maintain both the relative order of characters and the smallest lexicographical order. The frequency dictionary ensures that we don't prematurely remove characters that are still needed for the result, while the set in_stack prevents duplicate entries in the final string. Let's briefly analyze the data structures and their space complexity. The dictionary frequency requires constant space, as it tracks at most 26 lowercase English letters. The set in_stack also has constant space usage for the same reason. The stack, on the other hand, has a space complexity proportional to the length of the input string, specifically O(n). For time complexity, the algorithm runs in O(n), as each character is pushed and popped from the stack at most once. This makes the approach both time and space efficient for solving the problem. It's important to consider edge cases to ensure the algorithm handles all scenarios correctly. For instance, if the input string is empty, the result should also be an empty string. If all characters in the string are distinct, such as in ABCD, the result is simply the input itself. On the other hand, if all characters are the same, like AAA, the result should be just one instance of that character, A. When characters appear in reverse order, such as tba, the algorithm will rearrange them to produce the smallest lexicographical order, resulting in ABCD. Let's walk through an example with the input s equals backtrack. Initially, the frequency dictionary is C4, B2, A1, D1, while both in_stack and stack are empty. As we iterate, we decide whether to push or pop characters based on their lexicographical order and frequency. For instance, when encountering A, we remove B and C from the stack because they appear later and are greater than A. Following this process for all characters, the final result becomes ACTB. The provided solution implements an efficient algorithm to solve the remove duplicate letters problem using a greedy approach with the help of a stack. First, we initialize a stack to build the result and a set scene to track which characters are already included in the stack. We also compute a dictionary last_occurrence that maps each character to its last index in the string. The algorithm iterates through the string using a for loop. For each character, we first check whether it is already in the stack, tracked by the scene set. If it is, we skip the current character since we do not want duplicates. Next, we ensure the stack maintains lexicographical order. While the stack is not empty and the current character is smaller than the character at the top of the stack, and the top character can still appear again later in the string, as determined by last_occurrence, we remove the top character from the stack. This ensures that the resulting string is lexicographically smallest. We also update the scene set to reflect that the removed character is no longer in the stack. After processing the conditions, we add the current character to the stack and mark it as seen. Finally, we join the characters in the stack to form the result string and return it. This algorithm runs in O(n) time, where n is the length of the string, as each character is pushed and popped from the stack at most once. Here, we start by importing the necessary libraries and defining our solution class. The method remove duplicate letters is where the logic resides. First, we create a stack to help us construct the result string in the correct order. Additionally, we use a set called scene to keep track of which characters are already in the stack, ensuring we don't add duplicates. A map named last_occurrence is also initialized to store the last index of every character in the input string. This map lets us know if a character can still appear later in the string. The first loop populates this map by iterating through the string and recording the position of each character. Next, we start processing the string character by character. For each character, we check if it has already been added to the stack using the scene set. If it has, we skip further processing for that character. Otherwise, we enter a loop to maintain lexicographical order. In this loop, we compare the current character with the top of the stack. If the top character is larger than the current one and can still appear later in the string, we remove it from the stack. This ensures the final result remains in sorted order while preserving the smallest lexicographical sequence. Once the stack has been adjusted to maintain lexicographical order, we remove the popped character from the scene set. Then, we push the current character onto the stack and mark it as seen so that it won't be added again. After processing all characters in the string, we build the result by iterating through the stack and appending each character to a string builder. This ensures that the characters are concatenated in the correct order. Finally, we convert the string builder to a string and return it as the result. This implementation efficiently handles the problem by leveraging the stack to maintain order, the set to avoid duplicates, and the map to track the positions of characters. The time complexity is linear, O(n), since each character is pushed and popped from the stack at most once, and the operations involving the map and set are constant time on average. Here, we start with the input string s equals cap. The first step is to prepare for our algorithm by initializing 3 variables. The stack is an empty list where we'll build our result incrementally. The scene set keeps track of which characters are already in the stack. The last_occurrence dictionary maps each character to its last index in the string, which helps us decide whether a character can be safely removed from the stack. For this input, the last_occurrence is computed as B3, C4, A2. Now, we process each character. At index 0, the first character is B. Since B is not in the scene set, we add it to both the stack and scene. After this step, the stack contains B, and scene is B. Next, we process the character C at index 1. Similarly, C is not in the scene set, so we add it to both the stack and scene. The updated state is stack equals B, C, and scene equals B, C. Moving to index 2, the character is a. Since it is not in scene, we check whether the top of the stack can be removed. The top of the stack is C, and since C and C appears later in the string, at index 4, we remove C from the stack and scene. Now, the top of the stack is B. Since B and B also appears later, at index 3, we remove B as well. Finally, we add it to the stack and scene. The updated state is stack equals a and scene equals a. At index 3, the character is B. Since B is not in scene, we add it to both the stack and scene. The state updates to stack equals a B and scene equals a B. At index 4, the character is C. Again, C is not in scene, so we add it to the stack and scene. Now, the stack contains a B, C, and scene is a B, C. After processing all the characters, we join the stack to get the result ABC. This completes the first example. Moving on, we will now examine the second input string, s equals backtrack. For the input s equals backtrack, we begin by initializing the variables. The stack is empty, scene is an empty set, and last underscore occurrence is calculated as C7, B6, 2, D4. At index 0, the character is C. Since C is not in scene, we add it to both the stack and scene. The updated state is stack equals C and scene equals C. At index 1, the character is B. As B is not in scene, we add it to the stack and scene, resulting in stack equals C, B, and scene equals C, B. At index 2, the character is a. Since it is not in scene, we check the top of the stack, which is B. As B and B appears later in the string, at index 6, we remove B from the stack and scene. Now, the top of the stack is C. Since C and C also appears later, at index 7, we remove C as well. After removing these characters, we add it to both the stack and scene. The updated state is stack equals a and scene equals a. At index 3, the character is C. Since C is not in scene, we add it to the stack and scene. The state updates to stack equals a C and scene equals a C. At index 4, the character is D. Since D is not in scene, we add it to both the stack and scene. The updated state is stack equals a C, D, and scene equals a C, D. At index 5, the character is C. Since C is already in scene, we skip it. At index 6, the character is B. As B is not in scene, we add it to the stack and scene. The state updates to stack equals a C, D, B, and scene equals a C, D, B. At index 7, the character is C. Since C is already in scene, we skip it. After processing all the characters, we join the stack to get the result ACTB. Finally, we consider the input string s equals ABCD. We initialize the variables as before, stack equals, scene equals set, and last underscore occurrence equals 0, B1, C2, D3. Here, we process each character in the string. Since none of the characters of B, C, or D are in the scene set, we add each one to the stack and scene. The final state after processing all characters is stack equals a B, C, D, and scene equals a B, C, D. Joining the stack gives us the result ABCD. This example demonstrates the simplest case where the input string already contains unique letters in lexicographical order. The time complexity of this algorithm is O(n), where n represents the length of the input string s. Let's break this down step by step. First, we have the pre-computation of the last occurrence dictionary. This step involves a single pass through the string using the enumerate function, which iterates over all characters exactly once. Each insertion into the dictionary is an O(1) operation, so the total time for this step is O(n). Next is the main loop, where we iterate through each character in the string. This loop runs exactly n times, as we process each character once. Inside this loop, there's a while loop responsible for maintaining the lexicographical order of the stack. The key observation here is that every character is pushed onto the stack at most once and popped from the stack at most once. This means the total number of stack operations, including both pushes and pops, is also bounded by O(n). Now, let's consider the other operations within the algorithm. Checking if a character is in the set scene is an O(1) operation. Similarly, adding or removing elements from the set is also O(1). Since these operations are performed at most n times, once for each character in the input string, their overall contribution to the time complexity remains O(n). Combining all these steps, from the pre-computation of the last occurrence dictionary to the stack and set operations, the total time complexity of the algorithm is O(n). For space complexity, the algorithm primarily uses three data structures: the stack, the set, and the dictionary. The stack stores characters from the input string, and in the worst case, where all characters are unique, the stack will grow to a size of n. Therefore, the stack requires O(n) space. Additionally, the set scene is used to track the characters currently present in the stack. Its size is directly proportional to the size of the stack, so in the worst case, it can also store up to n elements. This means the space used by the set is O(n). The dictionary, last_occurrence, stores the last occurrence index of each character in the string. While the number of entries in this dictionary depends on the number of unique characters in the input string, it is bounded by the size of the input alphabet. For lowercase English letters, this size is fixed at 26, making the dictionary space usage O(1) in this specific context. However, if we generalize to an arbitrary alphabet, the dictionary could require O(n) space. Finally, the result string is constructed from the stack, and its length is equal to the number of unique characters in the input string, which contributes an additional O(n) space. Therefore, the overall space complexity of the algorithm is O(n). To understand the efficiency of this approach, let's compare it with the brute force solution. A naive method to solve this problem would involve generating all possible subsequences of the string that contain all unique characters, sorting these subsequences lexicographically, and then selecting the smallest one. This approach is computationally prohibitive as it requires O(2 to the power of n) time to generate all subsequences, followed by additional time for sorting. Such an approach becomes infeasible for large inputs due to its exponential growth. In contrast, the current algorithm uses a stack and a greedy strategy to achieve linear time complexity, O(n). By maintaining the stack and ensuring lexicographical order through condition checks, the need for generating subsequences or performing expensive sorting operations is completely avoided. This makes the optimized approach significantly more practical and efficient for real-world applications. Now, let's analyze the algorithm under different scenarios. In the best case, the input string is already in lexicographical order and contains no duplicate characters, such as ABC. Here, the while loop never executes, and each character is simply added to the stack once, resulting in O(n) time complexity. For the average case, the input contains duplicates and some lexicographical order violations. While the algorithm processes all characters and performs a reasonable number of stack operations, the overall complexity remains O(n). In the worst case, the input string is in reverse lexicographical order with all unique characters, such as ZYX. In this scenario, each character is pushed onto the stack and later removed once, meaning every character is processed twice. Even then, the total time complexity is still O(n). The mathematical proof for this lies in the fact that each character is pushed onto and popped from the stack at most once. Since there are n characters in the string, the total number of stack operations is bounded by O(n). All other operations, such as set membership checks and dictionary lookups, are O(1), confirming that the overall time complexity is linear, O(n). Here, we dive into some common mistakes that arise when solving this problem. First, we often see incorrect handling of duplicates. The mistake here is forgetting to ensure that each letter appears only once in the resulting subsequence. This directly violates the problem's constraints, leading to invalid results. Next, there's the inefficient brute force approach, where all possible subsequences are generated without pruning invalid candidates early. This is highly problematic because the number of possible subsequences grows exponentially as 2 to the power of n, resulting in extremely poor performance. Another issue is improper lexicographical comparison. For example, comparing strings as if they were numbers rather than considering the ASCII values of characters. This mishandling can produce results that are not in proper lexicographical order. Lastly, ignoring edge cases is a frequent oversight. Inputs such as empty strings, strings with repeated characters, or strings that contain only one distinct character must be handled carefully. Failing to account for these can lead to runtime errors or outputs that don't meet the requirements. Suboptimal data structures are another common pitfall. For instance, using arrays for operations that would be much more efficient with stacks or deques introduces unnecessary overhead and increases the complexity of your solution. Now, when it comes to interview scenarios, it's important to recognize key patterns in this problem. A monotonic stack approach is frequently the preferred method as it ensures both uniqueness and lexicographical order. The optimal solution here balances these requirements effectively. By using a stack, you can achieve O(n) time complexity, which is a vast improvement over brute force methods. To optimize further, a frequency map can be employed to track the remaining occurrences of each character in the string. This helps in determining whether a character can be safely removed from the stack. During interviews, it's important to articulate your thought process, especially when deciding whether to pop elements from the stack. Clearly explain how your conditions ensure correctness and maintain the constraints of the problem. Now, let's explore some related problems and alternative approaches. The most directly related problem is, of course, the one we're discussing here, 316, remove duplicate letters, where the goal is to remove duplicates while maintaining lexicographical order. Another closely related problem is 1081, smallest subsequence of distinct characters, which shares similar constraints and logic. Problem 402, remove k-digits, is a variation that focuses on forming the smallest possible number by removing certain digits, and it utilizes a similar monotonic stack approach. Lastly, problem 321, create maximum number, involves merging subsequences optimally and touches upon overlapping principles related to maintaining order. For alternative approaches, the greedy method with a monotonic stack stands out as the most efficient, offering O(n) time complexity, though it requires careful handling of edge cases. Dynamic programming is another option. While it may be easier for some to comprehend, it's less efficient, often running in O(n)² or worse. Finally, recursive backtracking is conceptually simpler but computationally expensive and is more suitable for educational purposes or small input sizes. Great job! We've tackled problem number 316, remove duplicate letters, and learned how to solve it efficiently with a greedy approach. Remember to practice similar problems to master these techniques. Thanks for watching, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!